Hi, everybody. There, that's better. Sorry. So today we are going to talk about Chapter 8, which is the last chapter that we will cover in statics. So we're going to talk, the topic of Chapter 8 is friction. And so we're going to talk a little bit about the generalities of friction, and then we're going to learn how to analyze a free body diagram and take into account frictional forces, and also sort of the difference between a frictional force and an applied force. So we're going to cover those ideas. We're going to work a problem from section 8.1, and then we will have another lecture on Chapter 8 that follows. This lecture number is, if we come over here, we are at lecture 30, so I'll write that on the board as well. We'll have another lecture 31 on friction, and then that will be it for Chapter 8. That will leave us 2 lecture periods to review for the final exam, and then the final exam itself, which of course we'll spend a little bit more time talking about. But if we go ahead then and we illuminate that this is statics lecture number 30, that will place us contextually within the framework of what we've talked about so far. All right, so having said that, to begin with Chapter 8, must be the end of the school year. I'm out of paper here, so I might have to use some leftovers. There we go. We're going to take a look at the document cam, and we're going to start talking about what friction is. All right. So basically, when we talk about friction, we're talking about an induced force when 2 surfaces move against each other, or move or attempt to move against each other. Now, this type of friction is actually called dry friction. There's another type of friction, fluid friction, that has to do with the viscosity of fluids, or the thickness or the relative resistance that a fluid exerts when either it's moving over something or when something is moving through it. But today we're going to talk about dry friction. Now, one of the things that we have talked about in the past is we've used the term that the surfaces in contact are smooth or rough. And smooth is basically the key word or the code for you don't have to account for friction. You don't have to account for friction. In other words, you're saying that the surfaces in contact are slippery enough that this is not a consideration. Rough, on the other hand, means friction is important. Now, in real life, friction is always important, but you can see that sometimes it's more important than others. For example, if you have a pan and you're going to fry an egg in it, and you put some butter in it first, all right? That means that that egg is not going to stick to the pan as much. And on the other hand, if you have a cast iron skillet, for example, and you don't put any butter in it, the egg is going to stick and kind of get messed up. So that has to do with friction. Now, we're not going to do any analysis of eggs, obviously, but we could talk about a block, for example, of ice sitting on top of a surface of ice. And if we push that, it's relatively easy to move. However, if we have a block of the same size and it's made out of wood, and the surface that it's sitting on is carpet, when we push on it, even though it's the same weight, we're going to have to push on it harder or with more force in order to get it to move. So basically what we have in terms of a free body diagram for any type of an object sitting on top of another object, in terms of a free body diagram, we have the weight pushing down, and we have something that is known as the normal force pushing perpendicular to the surface of contact. So in a case like this, where the surface of contact is horizontal, the normal force will be vertical. However, if we have a block sitting on an inclined plane, the weight is still pushing downward, but the normal force in this case is pushing perpendicular to the surface of contact. So in other words, the block, part of the weight of this block is going to help it slide down the block or encourage it to slide down the block, whereas this, we're going to have to do something in order to make it move, and that something is push against it. Well, depending on how rough this surface is, when we push, we're going to get some sort of a frictional force that opposes that motion. Similarly here, this component of the weight is attempting to push the block down, but some sort of a frictional force is going to be responding and attempting to push it off until we not to push it off, but to not allow it to move down the plane until we reach a point which is called impending motion, or on the verge of just barely starting to move. And at that point, whatever the component of weight is encouraging the block to move down the plane is overcoming the force of friction, keeping it in place. Now, there's something really important, and it sounds silly to say, but friction is a reaction to impending motion. In other words, friction is never going to overcome this and push the block up the plane. All that friction does is resists weight. So you can think about it, if you have a moving, if this plane moves, and if you tip it from horizontal to some angle where it begins to move, the responsive frictional force must have changed over that course of time as well. So if we're not pushing on this at all, there's no frictional force. If we start to push on it, friction opposes that motion until it gets to the point where the surface of contact is not rough enough, and the push will overcome the friction and it will exceed that, and then motion will start to occur to the right. But the friction itself will never be so great that it will push the force to the left. All right, so there's a chart that your authors draw that I think is pretty good, where we have a graph of the force of friction versus this applied force P. And we're basically talking about the first scenario here, where we have a horizontal surface, a force P, and then we have some sort of an oppositional force F. Well, if P is equal to 0, F is equal to 0 as well. But up to the point of impending motion, as we increase P, F increases at the same rate or to the same number until there is an impending motion. In other words, we are just on the verge of moving it. And then at that point, it actually requires a little bit or sometimes a lot less force in order to keep it moving than it did to get it moving. And at that point, the force of friction remains constant. The object is moving, and that force is called the force F sub k, or the force of kinetic friction. Here you could call it the force of static friction. Okay, so in other words, it's not constant while the object is at rest. It is just equals response to how much P there is until P is overcome and motion becomes impending. All right, well, it turns out that frictional force is a function of how rough the surfaces of contact are, which is called mu, or coefficient of friction, and N, or the normal force. And since we've talked about there being two different kinds of friction, static, which they refer to in the textbook as F sub m, it's called maximum value. Let's say F sub s, let's say it goes from 0 to F sub m. That's more like it. So the maximum force of static friction is equal to mu s times n. This is a number that's determined experimentally. For example, Velcro has a higher mu sub s than does ice on clay tile, for example. F sub k, or the force of kinetic friction, is going to equal to mu sub k times n. And as we can see from this diagram, that remains the same. Once motion occurs, motion is occurring. Now, your authors also have a table that shows some approximate values for the coefficient of static friction. So you can think about this. Things that are slicker, metal on metal, have lower coefficients of friction than do things that are rougher, such as rubber on concrete or earth on earth. So these are ranges. You have to use a value, which will either be given or you'll be allowed to determine it in the problem, but we have to use one value in order to solve friction. All right. We also talk about the idea of an angle of friction. And the angle of friction, static, is referred to as phi sub s. And what that is the angle at which impending motion occurs. So once again, if we go back to this idea of a block sitting on a surface, and if we can tilt that surface, that inclined plane, to higher and higher levels or larger and larger angles, we'll get to a point where the block will begin to slide. And what happens at that point is the F sub m, that maximum force of static friction, is going to be equal to mu s times n. And if we divide both sides by that normal force, we get F sub m over n is equal to mu sub s. And this value is called the angle of the tangent, I should say, of the angle of static friction. Okay? Because if you think about it, if this is my phi, as I tilt it, wherever it starts to move is my phi sub s, we have a normal force that's acting this way. I'm going to draw a better picture in just a minute. And a frictional force that's acting this way, and basically the weight of that package that's pushing it downward. So I'm going to draw a better free body diagram on this. And we're going to say at impending motion. So we've raised that inclined plane to the point where it's just beginning to slide. We have, and we're going to call that phi. Right? So this is the weight. The weight has two components, but the weight going down the plane is going to be opposed by the force of friction. So the force of friction at impending motion is equal to mu s times n. We know that the normal force looks like this, and this is the weight in the normal direction, and this is the weight along the plane, so I'm going to call that W sub p. Now, if you do a little bit of trig here, if you notice that this line is perpendicular to this line is perpendicular to this line, if this angle is phi, this angle also has to be phi. So if I then do the summation of forces in the normal direction, which is perpendicular to the plane, and I know it's not moving up or down in relationship to the plane. I mean, it's not flying off or crashing into the plane. It's just always going to stay on that plane. I can then say that the normal force minus the weight in the normal direction has to equal 0. The normal force then equals the weight in the normal direction, and that itself is equal to the weight, this is the entire weight, times the cosine of phi. Okay? Okay, now along the plane, at that same, in the direction along the plane, which we'll call it P, at impending motion, that's also going to equal 0. So the force of friction here is about to be overcome by the weight along the plane. So at impending motion, those two things are equal. The force of friction is equal to weight. In this case, it's going to be times the sine of phi. And the force of friction itself is mu s times n. So mu s times n is equal to the weight times the sine of phi. Okay. All right, so the last thing we can do is to solve this for n. Since we have an expression for n up here, we can say that n is equal to w sine of phi over mu sub s. And then if we set those two things equal to each other, we can say weight times cosine of phi equals weight times the sine of phi over mu sub s. Weights cancel out. Cross multiply mu sub s is equal to the sine of phi over the cosine of phi, which is equal to the tangent of phi. All right? And this is what we found here when we talked about phi, and that is then where phi is the angle of friction. Right? And so this is equation 8.3 in your textbook. So the coefficient of static friction is equal to the tangent of the angle phi, where one package will begin, well, one object will have impending motion or just begin to slide against the other. All right. Now, since this isn't moving, we're going to call that phi sub s, static. And similarly, mu sub k, or the coefficient of kinetic friction, is going to equal the tangent of phi sub k. Oops, better scoot that up. All right. So the next thing that we need to do is to work a problem so that you have something in your notes as an example. And then I will assign a couple of homework problems for you to practice these skills. Okay. So let's take a look at problem. I'll do 8.1, and then I'll assign you 8.2, and maybe one more problem, 8.5. Okay? So your homework tonight will be 8.2 and 8.5, but I'll do 8.1 first. And it says here, the problem text says, determine whether the block shown is in equilibrium and find the magnitude and the direction of the force when P is equal to 150. All right, so what we have is an inclined plane, the angle of which is 20 degrees. We have an irregularly shaped block that's being pushed down upon with a force of 500 newtons. We're told that mu sub s is equal to 0.3 and mu sub k is equal to 0.25. We then push on it with a force of 150 newtons. All right, so some of the ideas we have here, this is really, it looks to me in the problem that is, the drawing implies that would be how much you're pushing down on the block, but I really think it's the weight of the block. Whatever it is, there's a vertical force of 500 newtons pushing on the block. There's a 150 newton force pushing on the block. There is a 20-degree angle, and what we're trying to determine is whether the block is in equilibrium. What equilibrium means is not moving. And what does that mean? Well, if this 150-pound force were to push it up, or this 500-pound force, that component of that would push it down, first of all, we would decide which way it would be moving. And then the next thing we would do is to decide if static friction, if F sub m is larger than that net value of forces, either pushing it up or down the plane. And then we would be able to determine if it's static. If it's not, that means it's going to move either up the plane if this is the more dominant force, or down the plane if this is the more dominant force. All right, so to draw a good free body diagram, I'm kind of exaggerating a little bit, but we have 500 vertical, 150 horizontal. We know that we have a normal force that is acting perpendicularly to the surface of contact, and we know we have a force of friction that is either up or down. We don't know which. The way that we're going to determine is the component of 500 newtons pushing it down the plane greater, or is the component of 150 pushing it up the plane greater? So let's just call these axes x bar and y bar in order to make that determination. We want to determine what the components are of this 500 Newton force along the plane. So I'm just going to draw that. I have this, but I want to turn that into x bar, or x prime and y prime. Okay, so I have 500 newtons this way. And as I said, this is perpendicular to this. This is perpendicular to this. Let me do it over here. It's a little bit better. So this is perpendicular to this. This is perpendicular to this. So if this is 20 degrees, this is also 20 degrees. So that means that the component of the 150, pushing it down, the plane, is going to be 150 Newton. I'm sorry, I'm doing the 500. So it's going to be 500 newtons, and we want to go down the plane, so that's opposite times the sine of 20 degrees. Now, what about pushing up? Let's draw another little diagram here. And here we're going to have 150 pushing it this way. So if we draw that same triangle where this is 20, we need to resolve this into along the plane and perpendicular to the plane. So here, using alternate interior angles, these two are parallel, so that means that this angle has to equal this angle. Okay, and so along the plane, this is going to be 150 newtons times the cosine of 20 degrees. All right, so I did not bring my calculator today, so I just need to find what those values are. The cosine of 20 degrees is 0.9397. And the sine of 20 degrees is 0.342. All right, so that means that the 150, the 500 Newton force, if I multiply those out, 500 times 0.342, this component is 171 newtons. And this component, I can see it's less because it's 150 times the cosine, which is 0.93 something, 9397. That value is 140.955, or 141. All right, so what that means is this is the force that wins. This is larger in value than this, so that means that just based on these two forces, the tendency is going to be for the package or the block to slide down the plane. That means that friction will oppose it going up the plane. All right, so now let's do summation of forces along the plane, which I've called the x prime direction, will be equal to 0 if it's not moving. So what we're really talking about is what is the maximum force of friction. So F sub m is going to equal mu s times the normal force. So that means that we need to determine the value of the normal force, and the normal force is in the y prime direction, and we know then that the summation of forces in the y prime direction have to equal 0, because it's not going to fly up or cave into the thing. The only motion it's going to have is restricted to the motion of the plane. All right, so if I think about it that way, and I think about this as being the negative, let's just think about this as being positive y prime going this way and negative y prime going this way. All right, so that means that I have the normal force pushing up, which is positive, and I have a component of the 500 Newton force pushing down. What is that component? Well, if this angle is 20, 500 looks like this. That angle's 20, so it's 500 times the adjacent cosine of 20 degrees. And then we also have a component of the 150-pound force, which perpendicular to the plane is going to be times the sine of 20, and the direction for that, if I draw it like this, 150 is right here. The component in the y direction is actually up, isn't it? So that's going to be plus 150 times the sine of 20 degrees. And those three things added together equals 0. All right, so I'm going to solve for my normal force. It's 500 times the cosine of 20 minus 150 times the sine of 20. All right, so once again, I need to find those values. The cosine of 20 is that 0.939. And when I multiply that by 500, I get normal force is equal to 469.84 minus the 150 times the sine of 20, which is 51.30. So if I take 469.84 and subtract 59.30, I get 418.5 newtons. All right. So now what we really need to see is it possible for F max to overcome that? So in other words, the maximum F sub m that I can get is mu s, which is 0.3, times the normal force, which is 418.5 newtons. And if I do that multiplication, I get 125.5. So that means that if the force of the 500 pushing down minus the force of the 150 pushing up exceeds 125 newtons, then the package will begin to slide down the slope. All right, so going back to my original drawing then, in the x prime direction, I have the force of friction, and I have 500 times, if that's cosine of 20 degrees, that's going down the plane, minus 150. I do that, 150, and this is going to be 20, so that's times the sine of 20. And then I have the frictional force pushing it up, minus, this is going to be, this is plus, this is minus, the way I have minus the frictional force actual equals 0. So if I have 500 times the cosine of 20, times the cosine of 20 is 469.84, minus 150 times the sine of 20. So this actually is, this is a minus, so it's blah, blah. So this is going to be minus F equals minus that plus this number 51.3. So I got minus F equals 469.84. That's 418. Okay, so force is equal to 400, the frictional force is equal to 418 newtons. All right, so that means that in order to not slide, the force of friction would have to be 418 newtons. And yet we found that the maximum force that friction can be is only 125 newtons. So the answer is no. The block, the system, let's say that, is not in equilibrium. So what that means is that block is going to slide down the plane. And once it starts sliding, we no longer use mu sub s, we use mu sub k, because it is kinetic, it is moving. All right. So what does that mean for us? This is a 20-degree angle. It says find the magnitude and direction. Oh, it doesn't ask us for anything more. But we could determine, so I guess that's the only thing that we want to know. This is the amount of friction. This is pushing it back up. This is sliding back down. And the question says, determine the magnitude and the direction of the frictional force when P is equal to 150. Okay, well what that means is the frictional force is not going to be equal to F sub m. It is rather going to be equal to F sub k, or the static, not static, but the kinetic friction. So it's going to be equal to mu k times the normal force. We determined that the normal force is 418.5. So we're told that the coefficient of static, or coefficient of kinetic friction is 0.25. So we have to multiply that by the normal force, and we get that the frictional force is 418 times 0.25 for a value of 104.6 newtons. All right, so that basically means that we're pulling up the block, or excuse me, we're opposing motion with a frictional force of 104, but we have the component of the 500 Newton force pushing it down, and we have the component of the 150 Newton force pushing it back up, but that it will in fact be moving down, and that this is the amount of friction that will be opposing that motion. All right, so that is an example of how to work a problem with dry friction. That covers the content in section 8.1. So I'll assign for you problem 8.2 and 8.5, which I'll put up on our Moodle page, and then we'll have one more lecture about friction on Wednesday, or I should say for lecture number 31, before we move forward and start reviewing for the final exam. Have a great day, everybody.